we'll look at the schedule right now. Okay, so let's look at the assignment 3 instructions first. If you click on it, let's open it up. So it's on Zoom, just in class in Zoom, just like the previous one. And the section 90 students will submit the videos just like last time. So the 4 steps that I outlined here. First is, go back. First is I would like you to identify 3 main problems with the current technologies. And many of you have already done this. I would say you get an option, you get a second opportunity to reiterate it or change it, okay, with current existing technologies. And if you already presented these, that's fine. You can simply reiterate them, maybe try to make it clearer. I made some suggestions on Tuesday. This step 2 is brainstorm solutions to the above problems. This is important, which means brainstorm, of course, on Zoom or Slack or Discord or whatever you want to use. Look at the 3 main problems and try to brainstorm. I would spend like half an hour to an hour excuse me, solutions to these problems. Be as creative as possible, but of course, please be wary of the laws of physics. And I want you to present a summary of your brainstorming session. What that means is basically you can list, and you can even write it down, take a picture of it. So when we do this in person, what happens is we actually stand around a whiteboard as you write these things down and take a picture of it, and you can submit that. So in this COVID situation, you can do this virtually on a whiteboard on Zoom, or just type it out, whatever, right? Let's put Alex in. Oops. No. Going back. Okay, so that's that, and maybe say a few things about each of the solutions. And hopefully you have a few solutions to each of the 3 problems. So 3 times 3, let's say, so like 9 things you want to discuss here, approximately. It's not exactly, I'm just giving you suggestions. And step 3 is to pick your top idea, which is essentially an innovation or a solution to the problem, to a problem or multiple problems. So you have to pick something that you want to focus on and maybe describe it in, not maybe, but describe it in greater detail. Clearly explain why you picked this one, why is it novel, and why no one has attempted it before, or if people have done it before, what issues did they face that you will try to overcome. You don't need to say exactly how you overcome, but maybe have an idea of how to overcome them. Okay, and I can help you with these if you have questions along the way. I know there will be lots of questions, but just get started early, because we're about 2.5 weeks away from this. And finally, present a preliminary analysis, including some simple calculations by hand, computer, whatever, or even simulations if you want, to add confidence to your proposed innovation. Be as quantitative as you can, but you can leave the detailed simulations and calculations for the next assignment. So this is kind of like laying the foundation, let's call it. Okay? Any questions about this?
I think someone is asking if it's 10 minutes. Tara is asking.
Exactly the same, yes, as last time. So this time, of course, we have to try to be on time. Last time everyone went over a little bit, which is fine. But again, my recommendation is make sure you practice, right? That's a common recommendation to everybody. And feel free to reach out to me, Apratham, on Slack if you need, guidance in any fashion. So we're both available to help you. Okay, I'm not monitoring the chat, so if someone sees something on chat, I would say just speak up, or someone else speak up on their behalf. I will try to monitor, but it's a little hard. Okay, let's see. The next announcement has to do with the instructions for running the ray tracing software. So we're going to use 2 types of ray tracing software, one using COMSOL, multiphysics, and one using Code 5 and Light tools. And both are very valuable, and there'll be 2 lectures on this next week. So, oops. Okay, so again, that's a good reason to be on time. So there are some instructions here on how to run the ray tracing software, but let me first ask, is Apratim on? Let's see. Apratim, are you on? I don't see him, not yet. Okay, so when he comes on, he will walk us through that. Let's take a quick look at the schedule and we'll jump into the lectures. So where are we? Oops. We are September 17th. Okay, so we're going to finish non-imaging optics today. And next week, we are going to focus on computer-based simulation of imaging and non-imaging optics. So it's important that at the end of the day today, you review, or before next week's lecture, you review what we have covered in terms of the basic theory. The imaging conditions, Snell's law, loss of reflection, basic stuff, okay? And so when you come in next Tuesday, you will see how to implement that in a computer. First using COMSOL, which is a bit more complicated software, I would say. It can do a lot of different things. And then using the Code 5 and Light tools, which is software for Synopsys. And we're fortunate to have Dr. Mary Kate from Synopsys giving a lecture next Thursday. So both by the way, you will have access to both these pieces of software for free, which is great as a U student. Just so you're aware, these things are typically many tens of thousands of dollars per year for a license, so they're very expensive. Then the week after that, we have assignment 3. So again, you'll really have only about 2 weeks to prepare for it. So please begin early, and the rest is so on. Any questions about all of that while we go to today's lecture? I'll make sure no one else is trying to come in. Okay, there's a question. Go ahead.
Just
yeah, go ahead.
Few things were left from the Apratim's lecture about geometric optics. So
yes.
So that because we are having our test on 17th October, I guess so.
Yes.
So that part should be there in the.
Yeah. So yeah, I am aware of what's remaining. So what is the exam will only cover what we have covered in class. It will only include what we have covered in the class. So if it's not taught in the class, it will not be in the exam.
Okay, sounds good.
So I just need to find the time to squeeze in the other stuff, the remaining part. But we'll get there. Don't worry.
Okay, thank you.
Okay, so let's begin where we left off last time. So just a quick review. What we found out is that if an imaging optic is, of course, doing, let me go back here. An imaging optic is doing a one-to-one map. So rays of light from point P will all converge to a point Q. That's a function of an imaging optic. Now, a non-imaging optic does something slightly different. It takes, it's here. You can think of this in many examples, but let's look at this particular example. So here you can see the system that we call a lens here is designed such that all the rays of light from a point E now gets focused to a point B, and all the rays of light from a point F get focused to a point A. Okay, so let me see if I should use my marker. Whoops, sorry. Oh, there's my marker. Yeah, so all the rays from E gets focused, all the rays from E gets focused to B, and all the rays from F gets focused to A. Okay, so that's the imaging part of it. That's a one-to-one map. But all these points in between are not focused to any particular point, except that by the principles of refraction, we can prove all the rays of light that come from those points in between E and F have to end up between A and B. That's not a one-to-one map, but it's a one-to-many map. Another way to say it is that there's an image of E is at B, and the image of F is at A, but any point in between, there is no image, but the power from any point in between ends up at any point in between A and B. And this is really the concept of imaging optics, non-imaging optics, sorry. Okay. So again, let me just read what this is saying. If the edge points E and F are imaged onto A and B respectively, then all the rays from the intermediate points between E and F must pass in between A and B. The lens then acts as a concentrator. No image is formed. There is no one-to-one correspondence between the points on the object and those on the receiver. In effect, this is a simpler design problem. Now, we're going to think about so this is a situation where the source is somewhat close to the lens, and we're going to think about a situation where the source now moves further away. In other words, we're going to move to infinity. Now, when you move to infinity, then the rays of light that this is emitting, like so, will now all become parallel rays, okay, as shown here. And those rays now get focused again to B, and these rays get focused again to A. This is, for example, the situation where you're trying to concentrate light from the sun, and the sun is really far away. Right? And then in that case, we define the angular extent, or it's a form of field of view, by theta. Okay, and it's symmetric. We're going to consider symmetry across this optical axis. This is referred to as the optical axis. Then by the previous principle, which is also referred to as the edge ray principle, which we'll come back to shortly, any rays in between these angles from minus theta to plus theta will end up between A and B. So the same condition that we just talked about in the previous slide is equally applicable, not just in space, but also in angle as well. Okay. Of course, they need not be focused, so they're not imaged, but they're simply in somewhere in between. Again, what we're trying to say is that if you take the edge ray from the sun and focus it to A, and the opposite edge ray from the sun and focus it to B, then all the rays in between must go in between. So the power from the sun can now be concentrated onto a solar cell, for example. Okay, so that's the idea. So this is the so-called edge ray principle. I will post a paper about all this also, so it'll help you to kind of follow. I'm going to talk more intuitively, but there's some math behind it, which I will post on the website. Okay, so the edge ray principle is a very basic idea that is used to design non-imaging optics. And one of the most important forms of non-imaging optics that we will come back to again and again is something called the compound parabolic concentrator. So we will refer to this many times. It's also referred to as CPC, just by its acronym. So first, let me play a quick video which explains what it looks like. So you have a picture. Okay, let's go here. Okay.
Want to collect and concentrate divergent light while avoiding the difficulties associated with multi-element system? If so, compound...
Can you hear the audio, or should I narrate it? Someone speak up.
We can hear it. We can hear
it. Okay.
Yeah, it's a little bit low, but...
Maybe the choice for you. A CPC is a concentrator.
Okay, that's fine. I will just narrate it. So let me go back. So this is what it. Okay, so that's what it looks like. Okay, that's the shape. It's a paraboloid, basically a rotated parabola across an optical axis. And you can see so if I pause here, I've got it's really slow. You can see what's happening at the bottom here is very bright, right? And that's because the light is being collected from the top, where the aperture is very high, and concentrated at the bottom. So you can already see the level of concentration, and we'll talk much more about this. Okay. Now, why do this? So it's a rotated parabolic shape. The wide end
a
collects the
rotated
divergent
parabolic
light,
shape.
and then it's concentrated at the
wide
narrow end.
of the CPC
And it has a
collects
defined
divergent light,
an
which
acceptance
is then
angle, which we
reflected
will
within
talk
the
about today.
CPC and concentrated at the
So you
narrow
can see what
output
it looks like. Now, what are they used for? They're
CPCs
used for, of
are
course,
defined
solar
using an
concentrators,
acceptance
as we will
angle,
talk about, but they're
which is
also
the
used in the
angular range
telecom
in which a
industry, for
CPC
instance, to
can
collect light from free space and
CPCs are ideal for any
couple
application that
into
requires
fiber,
condensing
optical
of
fiber,
divergent
for
light
instance.
sources,
So when you're watching your
and are
Netflix, you
commonly
can
used
actually
for solar
thank
energy
the
collection,
CPC
wireless
for
communication,
very
and
efficient coupling
biomedical and
of
defense
light,
research.
and many other things as well. So, so this device is actually, oops, what's that? This device is actually very useful for many things other than solar concentrators. Of course, we will focus primarily on solar stuff. So, okay, so let's think about what are we trying to do in the case. Let's take the particular case of solar concentrators. Okay, so because that's a simple idea and it's relatively easy to understand. What is the design goal? Our goal is to concentrate the incoming radiation to the maximum possible extent, okay, with the highest efficiency possible. So, okay, what does that mean? That means if you have a radiation source as shown in this picture here, okay, which is labeled E1, light emitted from that radiation source needs to be collected to the receiver, which, for example, can be a solar panel, which is labeled AB with very, very high efficiency. This is the goal, okay? So, of course, I can draw the rays of light coming from this radiation source and do something in between such that I collect the light. Okay, so that's again the goal. Now, what are we going to do? Now I'm going to flip it 90 degrees. So we want to increase the concentration factor. Okay, so if I look at this picture here, again, I have a very simple concentrator. I have a mirror labeled as, so first of all, let's first define everything. So AB, this thing right here is our solar panel, or we refer to as a receiver, or also referred to as the exit aperture, okay? Now, the incoming ray, we're gonna look at one ray of light for simplicity, which is labeled here by R1. So it's going straight down like that. Now, let's say we have mirrors to be able to concentrate it, as we saw in the case of the solar cooker. So the simplest case, I can put a mirror here, okay? This is BD1. That's a mirror. I have an angle beta. And what it does is it takes the ray of light, the angle of reflection is equal to the angle of, the incident angle is equal to the angle of reflection. The light simply bounces off and it reaches one end of the receiver, A. Now, if I say the ray R1 is the edge ray from the edge of my radiation source, I am redirecting that to the edge of my receiver. That is my edge ray principle. So let's imagine this is the edge ray from the receiver. I am redirecting that to the edge of my, not the receiver, from source. I am redirecting that to the edge of my receiver. Of course, because there is a symmetry here, which I haven't drawn until now, I can put another mirror here by AC, such that I have a completely symmetric situation with another ray, which goes here, which is easy to prove from congruence triangles. Okay, so I'm not going to go through that, but it's the exact same angle and so on. So this is the edge ray from the other side. I didn't draw it very well, but you get the picture. The light goes to the other edge. So if you want to maximize concentration, what do I have to do? I need to make this theta as large as possible. I need to be able to collect as much light as possible. Another way to say it, this angle beta must be as small as possible. So if you were to imagine the mirror, if I tilt it down, I'm going to open up the entrance aperture, right? So I'm going to change my color so we can see it a little better. This is my entrance aperture. Oops. Okay, that's my entrance aperture. Now, if I want to, and my receiver size is fixed, if I want to increase concentration, I need to increase the entrance aperture. In order to increase the entrance aperture, I need to bend this mirror down like that. So I need to reduce beta. Okay. So, and the entrance aperture C1, D1 must be as large as possible. Okay. Now, but if I make my beta too small, the edge ray R1 will miss the receiver as shown in this picture. Okay, if beta is too small, then this ray is not going to hit this edge. Instead, it will hit the mirror on the other side and escape the system. This is lost. That's not good. Okay, now I'm going to put you all in breakout rooms, and I want you to think about this problem. Innovate. How will you solve this problem? I want to increase this entrance aperture C1, D1. I don't want to lose the ray. What will you do? Okay, and I'll give you a minute, and let me put you in a breakout room right now. Hold on. Okay, you're going to spend a minute or so thinking about this. Okay, some of you are still not quite joined. Let me know if you have trouble. Still waiting for some of you to come back. I'm gonna make sure. Hold on. Okay, sorry, that was a little complicated, but does anyone have any good solutions that they want to share? Was there a problem coming back to the main room? Does anyone?
There was an issue right here with connectivity.
Huh, okay. Looks like a few people are still not out of the breakout rooms. Let
There
me
was
make
a
sure.
glitch.
I don't know. It was the same as last time, but let me just make sure. Let's give it a second. Few seconds. Hold on.
So you left me on the break room and I had to leave it. So the other times it took me automatically here.
Yes, I couldn't hear anything in the break room. Suddenly I thought that I am speaking only in the room.
Right.
Yeah, no sounds from anyone. I guess some connectivity problem or some technical issues in break room.
Okay, yeah, I just closed all the rooms. Hopefully some of you are able to come back.
Yeah, it's taking much more time than the previous
Yeah,
days.
must be the internet. Seems okay on my side, but I'm not sure. But okay, we didn't mean to take this long. So does anyone have an interesting solution to share? There are many ways to do this. Go ahead.
Oh, I think all you need to do is just change the angle of the right side. So the light bounced on the right side does not, reflected out from the left side. I think you tilted it a little bit even more to the right.
Okay, let's see if that would work. So
I,
again, yeah.
Or left. Wait, left.
okay, I think that in order to capture more light, we have to take beta small, but in case of to concentrate it on the other side, it needs to be tilted to the upper side above.
That's correct. Yes. So
Yes.
you have.
So I think for the same area, for the same area, the circle or like those curved feature will give the much more area than any kind of rectangular things.
Yeah, that's a good idea. We'll come back to that point. But does everyone visualize this? If we try to reduce beta, meaning bend it this way. Of course, that will move D1 this way and it will increase the aperture, so that's good. However, the ray of light will go over here and get lost from the system, so that's no good. So in order to recapture the ray, you have to push it back, which is the opposite of what you want, right? So the two competing requirements, and this is an engineering design problem, right? And there are many ways to do it. And I'm gonna show you the simple way, which is, you can think outside the box and I can add something to it, okay, which is what's going to show me. I added a new segment of mirror to it, as shown here, D1, D2. Now this new segment of the mirror can be at a different angle, beta 2, so, because it's shifted, right? It's shifted, such that I can still capture the edge ray. So the rays are the same angle. So this was the previous edge ray, R1, and this is the new edge ray, R2. Because I put in another mirror, I can bend it at a slightly larger beta 2, such that I can capture this. And you can see this, right, from the angle of reflection, from simple geometry. Okay, and on the other side is still the same, or if you look at R1, it's doing the exact same thing as before. Oops. Yeah. Okay, so that's the idea. Now, of course, on the opposite side, the exact symmetric thing happens as well, right? So there is a line of symmetry here, which again, I'm drawing right now. So everything is rotationally symmetric, or symmetry by reflection. Let's think about 2D for the time being. Now I can keep going, right? So I can, now my entrance aperture is C2D2, which is larger than C1D1, right? So now I've increased my concentration factor, which is how much of light am I collecting and concentrating. Because I've increased the aperture, I'm collecting more light. And I can keep going. I can keep adding more and more mirrors. And eventually, each of these mirrors essentially forms a continuous curve, because I can make these mirrors infinitesimally small. And as you've learned in calculus, I can make this into a locus of a curve. And if you work out the math, we can show that this is a parabola, or a section of a parabola, as you will see shortly. Okay, so I can keep adding these mirrors, and these mirrors can be infinitesimally small, and I can trace out a reflective curve. So this is a mirror. Okay, so all of these are mirrors, right? This surface is a mirror. And of course, there's a symmetry about here, just like before. So it's another mirror here. It's completely symmetric. And angle beta now is a function of the position. So it changes as you keep going up.
There is a chat, Professor.
There's some
There's a question. Okay.
Yeah.
Let's see. Feel free to speak up.
It was
If you continue to add more
by
sections, I think
next
rectangle
slide.
doesn't it limit toward the, yes, exactly, Cedric. That's exactly right. And we'll see that shortly in a picture. Okay, so what we will learn today is that this curve is also the curve that produces the smallest beta that's possible, and as a result, the largest entrance aperture, C3D3. Now, think about what is happening here. I have a set of rays of light coming into this system, right? And the rays of light can come at any angle, right? Within some cone of angles. And all of those rays are bouncing around within these two surfaces. The reflective surface A is C3 and B D3, and they're all ending up down here. That's exactly what I want to do, right? I have taken light from a very large aperture, C3D3, shown by here, and I've put it on a small receiver, AB. So I've concentrated the light with two parabolic reflectors. Now, as Cedric pointed out, these edge rays must get all the edge. This is a parabola because if you look at all these edge rays, now I'm going to rotate this picture. So I'm going to take this picture and rotate it, okay, by 90 degrees. And the edge rays which were coming here, right? These are the edge rays, now are coming straight down. Okay, so I've rotated everything a little bit. Hold on 1 second. So it's the same picture as before, simply just rotated. Now you can see that all the edge rays have to focus to one point, which is the exact same point as here. Okay. So F here is the same as the A there. And now it's very clear that this is the focus of a parabola. And we are only looking at a section of the parabola. The rest of the parabola is not drawn. It's out here. Okay. So now you can visualize what's happening. All edge rays must get reflected onto A, and the curve has to be a parabola. Parabola has its axis parallel to the edge rays. So this is the axis of the parabola right here. And it's parallel to the edge rays. And its focus is at F. Now let's put them all together. So there are two parabola, this parabola, and there's a reflected one on the other side. Put them all together. So let's focus on one parabola. So this is the one we just looked at, let's say. And this is the rest of it. So we can call this a truncated parabola, it's a solid line. And there's a reflected truncated parabola on the other side. And this forms the compound parabolic concentrator, or a CPC. And you can see the focus of the parabola on the right is over here. And the focus of the parabola on the left is over here. And the focus is where the edge rays get focused, exactly the same as what we talked about in the very first slide. Edge ray principle. So we're ensuring that the edge rays go to the edges of the receiver. So keep in mind, this is the receiver. Oops. Keep in mind, this is where you'll put the solar cell. So the edges of the solar cell are receivers, that are the two foci of the two parabolae. And any rays in between, we know by the edge ray principle, will end up in between. So that's why this is a theoretically best design, because you can mathematically show, at least in 2 dimensions, this is 100% efficient within those acceptance angles. So we'll talk about what this means now. Okay, so make sure you're able to visualize this. That's the important part. Now, one obvious question is, why did we stop extending the parabola? Why not keep going up, right? Why can't we just keep going up here? However, you will see, as if you keep going up, at some point, which is exactly at this point, it will start bending in, and it will shadow the edge rays coming from this side. Okay, which you can see, right? You can see on the other side, because it's a parabola, it has to bend in, and then it would block the light. So there is an optimum height to the CPC. They curve inward and the entrance aperture is decreased. Another way to see it is you can see that C4D4 is now less than CD, which is maximum aperture. So the geometric concentration actually decreases. Now, we'll talk about this term quite a bit, so let me emphasize this. Oops, sorry. We'll talk about this all the time. So there's something called the geometric concentration, or geometric concentration factor. Okay, this is simply the area of entrance aperture, which is the top, this thing here, divided by area of receiver, or the exit aperture, which is the bottom here. Our goal is to maximize this. Okay, of course we are drawing all this in 2 dimensions. So in 3 dimensions, the area. Right now it's just a line, but you get the idea. Okay, the edge ray principle, let's reiterate this because it's basically the simple but very fundamental concept in non-imaging optics. Light rays coming from the edges of the source must be deflected onto the edges of the receiver. This is a basic design principle of non-imaging optics. Again, just to reiterate, the edge ray goes to the edge of the receiver. Okay, so if you come in at an angle that's less than the edge ray, by the way, means the largest angle that you can collect, right? So the edge of the source. If you're coming at a smaller angle, as we know, it will end up at the receiver, somewhere in between the two edges of the receiver. But if you come in at an angle that's larger than the edge ray, which means it's outside what the CPC is designed to collect, you can see what happens is that the light bounces around, and you can actually show it will eventually leave the system, so it's lost. So all rays entering the CPC with an input angle less than theta will be trapped and collected at the receiver, and all rays with input angle greater than theta are lost from the system. So now I can make a plot of acceptance or acceptance efficiency, which is the number of rays reaching the receiver, or the number of rays accepted, divided by the number of rays coming into the CPC. And by the CPC being the ideal concentrator, has 100% efficiency, so this is 100% if the angle is between minus theta and theta, because we're looking at the two sides. If the absolute value is greater than theta, which is the acceptance angle, then nothing is accepted. And this theta is also referred to as the half acceptance angle because it's the half of the cone. Okay, and that's shown here. Also, we can show this very, very nicely using this very simple geometry. So for a general parabola, we know this fact. If you take, this is a locus of a parabola. When you learn geometry in high school, you've probably done this. You put a stake on the ground or a pencil fixed to a location, and a pin holding a string here, and then having a pencil moving if you move and draw it, that forms a parabola. I think all of you have done this. Now you can show that is simply, what that means is that the path length, which we talked about, by the way, a couple of lectures ago, from A to C plus C to F, which is shown here, it's C plus CF, is equal to the path length from B to D and D to F, shown here. Okay, you can actually show this mathematically, right? And this is also optically makes sense because this is the path that light takes if it comes in straight down like that, as it reflects off this parabola and reaches the focus. We know from the imaging condition that that's exactly what we also call the Fermat's principle. You may or may not remember that. We'll come back to this. Okay, now for the CPC, if you apply this condition, so you can see, let's look at the edge ray shown here. We can look at just one side. So CB, so let's follow the equation. Let me change the colors, easier to see. Okay. So CB plus A2. So CB is, by going down here, CB plus AB. Okay, that's CB plus AB is also A2, which is the size of the receiver, is equal to ED plus DA. So let's draw that. ED plus DA is ED plus DA. These two are exactly the same principle. Okay, if you rotate this parabola a little bit, you will see exactly what you're seeing here. And why did I pick E? This E is the normal to the ray, right? Exactly as we picked AB here. Okay, now we can do some simple geometry now. CB equals DA. So what's CB? CB is this line is equal to DA because of symmetry, right? That's easy to see. Let me erase some of these. It's not so messy. Okay, now I can put CB and DA can cancel out of this equation. then A2 equals ED. Now, ED, this distance here, is nothing but A1 sine theta, where this is A1, which is the entrance aperture, right? Sine of theta is simply this distance ED divided by A1. So now I get a very simple, very nice expression. A1 over A2 is 1 over sine theta. Now, what is A1 over A2? This is nothing other than the geometric concentration. A1 is the size of my entrance aperture, and A2 is the size of my receiver. So it's exactly what we just talked about 2 slides ago. This is my concentration. So a very simple expression now, saying that the concentration of my CPC is inversely related to sine of the acceptance angle, theta. In other words, if I want to accept more light, I have to give up on concentration. I have to concentrate less. If I want to concentrate a lot, I need to collect over a smaller range of angles. This is a very fundamental concept. It actually comes from the second law of thermodynamics, and we'll come back to this again. Very, very fundamental. Very fundamental thing in optics, which relates optics, by the way, to thermodynamics in a very fundamental fashion. Okay. For small acceptance angles, so if you were to concentrate a lot and this theta becomes very small, so you're trying to concentrate a lot and you're trying to make it into a you're trying to simply make the solar cell really, really small, then this height of the CPC becomes very tall. Now let's try to understand how that is. Again, with some simple geometry. H, the total height here, this is the height, H, is H1 plus H2, okay? Now let's see each term here. H1 is A1 divided by 2, which is this part here, A1 by 2, divided by tangent of theta. Okay, you can see this right angle triangle here. Okay, tan theta is A1 over 2 divided by H1. So H1 is A1 by 2 divided by tan theta. You can do the same thing on the other side for A2 over here. And you will get, H2 is A2 over 2 divided by tan theta, and you can put them all together and some simple algebra, you get this expression. So what's the purpose of this? As theta increase, so this is wrong. Theta should decrease here. It's a mistake. As theta decreases, H increases, which I hope you can all see, right? As theta decreases, tan theta increases and H increases. As theta goes to 0, H goes to infinity. Again, you can see this, tan of 0 is infinity. Tan of 0 is 0, so 1 over 0 is infinity. So for small acceptance angles, the CPC becomes very tall, which is problematic, right? You don't want something huge. So these are all design considerations and relatively simple concepts to understand. Now, of course, so far we've only talked about in 2D, but you can actually show that the CPCs what we have shown, not mathematically, but at least in a qualitative sense, you can prove this mathematically. CPC is an ideal concentrator in 2D. In 3D, it can be shown that this is not an ideal concentrator. Some of the skew rays are lost. So something you should be aware of. There are 2 ways to think about CPCs in 3 dimensions. You can simply rotate it, as shown here, which is what we saw in the video, or you can put slices of it, as shown here. Right? You can take a slice, 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 slice. So there are differences in the way you manufacture, and both have different performance as well. Depends on what you want to do. Oops. Wait a second. Okay. So, and we won't talk much more than that about this, except in the next part 2. So we're going to start the part 2. We'll talk a little more about the properties of CPC. Any questions so far? Okay, so Apratim, are you on? So let me see, does anyone see Apratim yet?
No, I guess.
Yeah, it doesn't.
Yeah, okay, that's fine. we'll look at those. Yeah. Okay, so let's forge ahead because we have to cover a bunch of things. So the CPC is an important non-imaging element, so we want to spend a little more time thinking about the properties of the CPC, like how to analyze them. Most of this is related to what you've done before and some simple geometry. So there's a little bit of math coming. But feel free to stop me if you have questions. Now, the CPC maximizes concentration. So let's look at this in a little more detail in 3 dimensions, okay? Actually 2.5 dimensions now. First, what does that mean? We are going to look at infinite CPCs, okay? Actually, this is 2 dimensions. So look on the right-hand side first. No, actually, let's start on the left-hand side, okay? So imagine we have a black body, which is cylindrical, so infinitely long, okay? At some temperature T, and it's emitting, right? It's emitting in all directions. It has a radius of r, and we're going to look at a unit length of this. And let's imagine also that this is embedded inside vacuum at 0 Kelvin. Okay, we're going to look at 1 unit length of it. We're calling this the source. And that we're going to put a cylindrical CPC or a 2-dimensional CPC at a distance d away from the source, as shown here. Okay, this is the CPC, and it's drawn like this because it's cylindrical, so it's infinitely long in that direction. And it's essentially acts as a linear concentrator with a concentration factor of C. Now let's think about this from a thermodynamics perspective. The flux emitted by the black body of a given area, dA, and temperature T into a hemisphere. So if I were to take this cross section and draw it, this, it's emitting in all directions, right? But we're only going to consider a hemisphere. Actually, should be a full sphere, not a hemisphere. This is emitting in all directions, so it includes both. Sorry, I didn't put I didn't divide it by 2. So, is sigma T raised to 4 dA? This is, as you recall, this is the Stefan Boltzmann law, right? This we talked about before, where sigma is the Stefan Boltzmann constant and T is the temperature in Kelvin. And dA is the area of this emitter on the left-hand side. Now, a black body of length Lu emits flux given by the area of this, which is 2 pi r times Lu. That is the area of the cylinder. So this is the radius. Oops, actually, I should draw it slightly differently. This is the radius r, and Lu is the length of the cylinder. So it's like a cylinder, right? Like this. Now we're going to say Lu is 1, so it doesn't matter. But 2 pi r is the surface area of the cylinder. That is this dA. Okay. Now flux emitted per unit length, like I said before, we're going to set Lu equal to 1. So you get this nice expression, 2 pi r sigma T raised to 4. That's what's coming out of the source. Now we're interested in what we can collect. Now we're going to look at a cross section, which is shown here. Okay, so the source is on the left-hand side. Let's say it's a big sun. Okay, it's emitting light in all directions. Of course, the 2-dimensional sun. And then we're collecting light on this side with the CPC. Okay, so first of all, you notice the marginal ray is the edge ray intersecting at an angle theta to the optical axis of the CPC. And you also notice that A2 is the size of the solar cell or the exit aperture of the receiver, and A1 is the size of the entrance aperture, just like before. The amount of radiation the entrance aperture A1 receives per unit length is simply related to the distance at which this entrance aperture is relative to the source. We also talked about this. Venus receives a different amount of radiation than the Earth, for example, because of the distance from the sun, right? So that's basically what this is. And you can simply divide because it's in 2 dimensions, there's no square here. It's just the ratio of the R divided by D, R being the radius of the source, D being the distance from the source, times A1, which is the intersection, how much of the light is intersected by the area of the entrance aperture of the receiver. Of the CPC. So again, just to be clear, this is the CPC. Okay, I think so far so good. It's just all this equation is saying is that out of the sigma t raised to 4 2 pi r, which is what's emitted, which we saw here, right? 2 pi r sigma t raised to 4 shown here. I am collecting some fraction of it, which is the fraction is simply r divided by d, because I'm spreading the light over a big circle, big 2D circle, multiplied by the area of the length of the entrance aperture. Okay, that's this factor. Now assume that there is a black body that absorbs radiation at the exit aperture, which is our solar cell, let's call it. The temperature of this black body has to be less than T, because right now we are assuming that everything else is vacuum. Okay, so there's no other energy source to heat up the source. But at equilibrium, it will thermalize, it will reach a thermal equilibrium with the source, which will be the same temperature as the source, T. So we can also say that the solar cell or the receiver we place at the exit aperture will also emit radiation with the flux per unit length given by sigma its area, A2, times T to the power 4. Again, we're looking at a unit length, so we're ignoring the L there. Okay, now under thermal equilibrium, so again, let me very clearly make sure everyone's clear what we're talking about. The solar cell at the bottom of the CPC is also a black body, right? It has some temperature. So it's also going to emit light, photons. And the CPC is the system in between, and the source is also emitting photons. Now the CPC is collecting some of these photons, which is phi, right? And this emission is phi 2. And assume that the solar cell or the receiver is simply connected to the CPC, so the light cannot go anywhere else. So phi must be equal to phi 2, otherwise this whole system will increase in temperature, so it won't be in equilibrium. So if it's in equilibrium, phi and phi 2 must be the same. And if so, I can put these two equations the same. And I get a very nice simple expression, A1R over D is A2, or A2 equals A1 sine theta, which is exactly the same as what we saw before. So now, from purely thermodynamic considerations, we have proven what we proved in the last 10 minutes or so with purely geometric considerations, which is not a rigorous proof, but is another way to show that the CPC is an ideal concentrator. So let me reiterate what does that mean? Since the rest of the space is 0 Kelvin, radiation leaving A1, which is the entrance aperture of the CPC, and coming from A2 can only be headed to the source. This implies that the acceptance, so in other words, if the light is leaving A1, there's nothing else for it to go to, it has to go to the source, which is SR. This implies that the acceptance angle of the CPC with the entrance aperture A1 cannot be larger than theta. In other words, the rays that are coming in must match the rays that are going out, both in flux and also in angle, which kind of also makes sense if you just simply think about time reversal as well. Now, as D goes to infinity for a constant theta, in other words, if you're looking at something really far away, this radius R also gets very large, this small radius R. Then A1 becomes a straight line. So instead of being instead of being a curve like that, it becomes a flat line. And the concentration factor simply becomes, this is A1, this is A2, A1 over A2, which from the previous expression here is simply 1 over sine theta. This is the maximum possible concentration for 2 dimensions. Same as the CPC. So we conclude that this is by the way, this is the maximum possible concentration in 2D from a thermodynamic perspective. So this is basically a law of physics. Because the CPC can achieve this, we can then say that CPC gives a maximum possible concentration of 2D. In other words, our CPC is the best possible concentrator. It may not be the only possible concentrator, but it is the best possible concentrator. It is one of the best possible concentrators. To prove that it's the only possible concentrator is a much harder problem. Okay, so we can do the same argument in 3 dimensions, which is, of course, in real life, everything is 3D. So we have to make this argument in 3 dimensions. So again, the arguments are very similar. So the source is now a sphere like the sun, and it's emitting in the entire spherical domain. And the CPC is three-dimensional CPC, and then there's a receiver at the bottom. Now we talk about A1 as the entrance aperture area and A2 as the exit aperture area. Okay, so flux emitted by the spherical source SR is now 4 pi r squared sigma T raised to 4. Of course, we all know that the 4 pi r squared is simply the area of the surface of the sphere. The radiation captured with the entrance aperture A1 is again just like before, the square, the fraction that is spread over the entire sphere, the big sphere, which is defined by this distance d. Okay, so that is the r squared over d squared. Now you have the square because it's area now, not a line like you did in the 2D case, multiplied by the area of the entrance aperture. So exactly the same argument as before, except that now you have in 3 dimensions, so you get the square. This will get concentrated onto a black body at the exit aperture A2. Again, we make the same argument at thermal equilibrium. This black body heats up to T, and the radiation that A2 emits must equal that it receives. And we get this, again, a simple expression. This is the fraction that's going in. This is our phi, and this is our phi2, A2 sigma T to the power 4. And then putting them all together, you get a nice expression. A1 over A2 is d over r squared, or A1 over A2 is 1 over sine squared theta. So in 3 dimensions, it's 1 over sine squared theta. In 2 dimensions, it's 1 over sine theta. Making the same geometric arguments as before, d goes to infinity, r goes to becomes very large at a constant theta. A1 tends to be a flat surface. All that's saying is instead of having this curved surface here, this simply becomes a flat surface. Not terribly important, but it's just an approximation that allows us to essentially prove that this, by the way, is the concentration factor, right? A1 over A2. So again, you see in 3 dimensions that the concentration factor is inversely proportional, not to this 1 sine theta, but to sine squared theta. So it's more sensitive. Oops. Now, if the black body is immersed in the concentrator, in other words, if you have a refractive index that is that's larger than 1, then you have to take that into account. This becomes important in certain situations. For example, if you had, let me see if I can draw it. If you imagine you had a solar concentrator, CPC, I'm gonna draw it something like that. But now I put like this concentrator is filled with some material, let's say water, okay? Where refractive index is 1.5. That behaves a little bit different than if it was not filled with water. And you can actually show by filling it with a water or some higher index material, you get an increase in concentration factor by a factor of n squared. Now this becomes very important in certain applications, for example, in heliostats and so on. We'll talk about that later. But just be aware, you don't need to memorize any of these equations, of course, but just be aware that there is the Stefan Boltzmann constant, sigma, depends on n squared, which we saw before, but it just means that it is n squared times the vacuum Stefan Boltzmann constant. Now, if you plug in all the numbers, what you see is that the concentration ratio is now n squared over sine squared theta, as shown here. Okay, and in 2 dimensions, you can do the exact same thing, and you'll see that it's n over sine theta. So it's a potentially an easy way to increase the concentration factor without giving anything up. However, what you give up, of course, is the fact that if you fill this thing with water, it's going to get heavier. So that's something you have to deal with. Sometimes you don't want to do it. Now, of course, you can understand this whole thing, whole business of refractive index without invoking thermodynamics at all. By the way, this equation comes from Planck, quantum theory, from Planck and thermodynamics, by the way. So they're both related together. However, you don't need to invoke any of that. You can actually show this from simple Snell's law, right? Let's think what I mean. Let's think how to do this. So imagine I have a ray of light coming in at an angle, theta. Okay, that's theta, so the full angle is still theta. If I have air outside, this is an index of n. I know my ray will bend in at an angle such that n sine theta star is sine theta, where this is now theta star. Okay, everyone knows this by now. This is a simply angle of reflection. and then light reflects to the other edge of the receiver, this point here. Now I can write down, okay, this is just Snell's law. I can now write down A sine theta star is A2 because we can do geometry, right? We did this inside this material. We know that A1 over A2 is 1 over sine theta star, just like we did before. So simply plugging these two equations in here, we will get A1 over A2 n over sine theta. So what we did invoking thermodynamics, you can also simply do it with Snell's law and some simple geometry. Okay. Okay. The last thing I want to talk about is just an example of how this is done of a paper. So I think I'm pretty much done with the basic. So these are the basic concepts of non-imaging optics. So you basically have all the tools, and we'll give a few examples. But I want to show one example of a paper that came out in Nature a couple of decades ago, again written by this professor called Roland Winston, who's considered the father of the field. Essentially, he was able to design a system and build a system which showed the radiance on Earth that exceeds that on the Tycho, sun's surface. Okay, so it's a very interesting paper, and let's see how they do it. So let me see. Okay. So first of all, let's read what it says. The flux at the surface of the sun is 6.3 kilowatt per centimeter squared. So it's a lot. We saw that. It falls off the square of the distance to a value of about 137 milliwatt per centimeter square above the Earth's atmosphere because of the propagation through space, the distance, and typically about 80 to 100 milliwatts per centimeter square at the ground. The second law of thermodynamics permits an optical device to concentrate the solar flux to obtain temperatures of the Earth's surface not exceeding the sun's surface temperature. However, imaging designs are inefficient and so on and so forth. But you can improve the design by a factor of 4 or more and approach the thermodynamics limit by using a particular kind of non-imaging design and also an increase in the refractive index, which is shown here. So let's look at how it's. So first, they have a system. You have sunlight bounces off this 40 centimeter mirror and focuses on a silver cone. So you can see the silver cone is here. Okay, so sun is here. This is the mirror. Okay, now silver cone squeezes light from 1 centimeter to about 1 millimeter. And then the light here is about 60,000 times brighter than normal sunlight. And the silver cone is essentially the CPC. So this is a detail of the silver cone. And what they did is that here they put, so this is exactly the same as before. You have this is the mirror. And this is the CPC, essentially. And they have a calorimeter to measure the temperature. And you can see some details here. So this image of the sun is formed here, but because they can fill it, there's a lens to collect the light onto the calorimeter and then measure the temperature. So this was a very interesting example where they showed that you could measure a temperature on Earth that was higher than the temperature on sun, just by using sunlight, which should not have been possible if you really think about it. The only reason it's possible because of that increase in proper design of the non-imaging optic, but also increase in the refractive index of the material used. At this stage, I will stop, but I'll point out to a very interesting TED Talk, actually, by Bill Gross, which I posted a link to on the website. So I encourage all of you to read it. It talks about non-imaging optics and some application. It's a few years old, but it gives some really interesting and useful information. And I'm going to leave you with actually, I don't have it. I had a practice problem, but today I didn't think I would have time. So I'm gonna stop it. And actually, we're gonna end a little early for a change today. But before we end, I'm gonna first ask if there are any questions. I know I covered through a bunch of simple geometry and thermodynamics quickly, so make sure you go back and review it. And again, the key point is make sure you review the imaging optics part of it, geometrical optics part of it before next Tuesday, because we're gonna start doing these simulations on the computer. Okay, so for those of you who came in late, I posted instructions for assignment 3 here. It's due in 2 weeks. So this is the part that I don't have up with them here, but I just want to make sure you go through it because you will need it on Tuesday. Let me make sure it's up with them here yet. No. Okay, so I will go through it. So this, you don't have to do it, but will be very helpful before you come to class on Tuesday, before you come to Zoom class on Tuesday. We're going to use COMSOL multiphysics for ray tracing, and I put them prepared some instructions here for what you need to do to prepare if you want to run the simulations along with him when he goes through the lecture. So first of all, you need to download the VMware Horizon client, which allows, oops, go back, sorry. Wait, what happened? Sorry, I don't know. Okay, so in any case, you should download this because it allows you to do the remote login and run the software remotely from the Kate lab. If you have trouble with this, of course, reach out to me or up with him, and basically we'll put you in touch with the College of Engineering computer folks who are fantastic in supporting us for this. But there's some detailed instructions here. I'll encourage you to go through it and make sure you're able to log in if you haven't done so already. And the rest will be gone in class, how you run it and so on. Again, Apratham will go through this in class on Tuesday, but if you have access to a computer that you can run this, of course, you're going to run this remotely, so you don't need a very powerful computer. But if you're able to do this, that will be useful. Okay, with that, I guess we're done. Any questions?
Why do we need a VMware to run the software? I'm trying to understand.
I think that's the way it's set up at the CADE lab, which is the College of Engineering's computer lab. I don't know the details of it. I'm not a computer networks person.
Yeah.
But my understanding is that it allows you to do the virtual environment to run this.